This is section 1.3, B, analyzing graphs of functions and relations. By the end of this video, you should be able to explore symmetry of graphs and to identify odd and even functions, as well as see the relationship between symmetry and odd and even functions. So let's start with symmetry. There are two different types of symmetry. And let me just move this over. There are two different types of symmetry. So graphs with line symmetry can be folded along a line so that two halves match each other. And then we have something called point symmetry, which is also called rotational symmetry. So point symmetry is also called rotational symmetry. Rotational symmetry. And what that means is that it can be rotated 180 degrees with respect to a point and appear unchanged. For all intents and purposes, the rotational symmetry that we're going to be talking about is symmetry with respect to the origin. So you can take a graph and rotate it 180 degrees about the origin, and what you should get back is a picture of the same graph. So there are ways that we can test for different types of symmetry. So we have three different tests. So first off, we have symmetry with respect to the x-axis. We have symmetry with respect to the y-axis. So let me highlight some things for you. I have symmetry with respect to the x-axis, symmetry with respect to the y-axis, and as I said, we have symmetry with respect to the origin. And this is going to be our rotational symmetry. But the graph of a relation is symmetric with respect to the x-axis if and only if, for every point xy on the graph, the point x negative y is also on the graph. So if we want to look at a function model, if this is my point xy, it will have symmetry with respect to the x-axis if the point x negative y, or if I just negate the y coordinate, that point will also show up on the same graph. And then the way that we verify this algebraically is that if we take our equation, if we're given an equation, and if we substitute in negative y into the equation, we should get back the same equation. Similarly, if we have a graph with the graph as a relation is symmetric with respect to the y-axis if and only if every point xy on the graph, the point negative xy is also on the graph. So it's very similar to respect to the x-axis. If we're on a graph, or this is my example here, if this is my point xy here, if I negate the x-coordinate, I should be able to find another point that is still on the same graph. And similarly to the algebraic test for symmetry with respect to the x-axis, if I plug in negative x into my equation, I should get back the original equation. Finally, we have something called symmetric with respect to the origin, and that is that a graph of a relation is symmetric with respect to the origin if and only if, for every point xy on the graph, the point negative x negative y is also on the same graph. So in my model, if I take my point xy here and I negate both coordinates, if that point is still on the same graph, then the graph itself is actually symmetric with the origin, which it has rotational symmetry, which means I could take this graph and turn it 180 degrees either way, and I should get the same graph back. Algebraically, what that means is I'm going to take x and y, I'm going to substitute them with negative x and negative y, and see if I get the same equation back. So let's try an example with it. If I look at the graph of this function, so I'm going to use the graph of the equation to test symmetry with respect to the x and y axis and the origin, and I'm going to just support numerically and confirm algebraically. So for example, if I look at the graph of this function, which says x minus y squared, and this is actually not a function, this is just a relation because it fails the vertical line test. If I look at the graph of this relation, which is x minus y squared equals 1, it looks like this graph actually has symmetry with respect to the x-axis. And so the way that we test this numerically is that I pick a point xy, and so if I look, if this is my point 2, my x-coordinate 2, well, if x equals 2, then I can say that y is going to equal, so let me plug in, it'll be 2 minus y squared equals 1, so be negative y squared equals negative 1, so y is going to equal positive 1. So this is going to be the point 2, 1. And what I should be able to do is see if I can get this point. This should actually be plus or minus 1 since I took a square root. So this should be the point 2, 1, and this point should also be the point 2, negative 1. And that's going to tell me that this is symmetric with respect to the x-axis. So I have the same x coordinate, but with y coordinates that are essentially numerically the same, they just differ in sign. And I could pick any one of these points and calculate it, and it would still work out to be the same way. To confirm algebraically, what we're essentially going to do is that we're going to take negative y and plug it into this equation and see if I get back the original equation. So what I mean by that is we're going to take x minus y squared equals 1, and then I'm going to substitute negative y into the equation to see if I get back the same equation. So that would look like x minus negative y squared equals 1. But I already know that if I take anything and I square it, I'm always going to end up with a positive. So x minus negative y squared is really just the same thing as saying x minus y squared equals 1. And since this equation and the original equation are the same, that means that this graph, or this relation, is symmetric with the x-axis. Let me try one more. Now I have the equation xy equals 4. This is the graph of a hyperbola, which we'll talk about later when we start talking about conic sections. But if I look at my point, if this is the point 2, 2, and it doesn't look like it has symmetry with respect to the x-axis or symmetry with respect to the y-axis, but it does look like it might have symmetry with respect to the origin. So in order for it to have symmetry with respect to the origin, I'm going to take any xy coordinate and I'm going to negate both coordinates and see if the negation of these two coordinates is also still on the graph. So the negation of this would be negative 2, negative 2, and if I look on my graph, this is the point negative 2, negative 2, and it is on the graph. So if this is xy, then this is the point negative x, negative y. So that supports the assumption or the assertion numerically, but let's actually just justify it algebraically. In order to justify something algebraically, or to say that this function is symmetric with respect to the origin algebraically, all I have to do is wherever I see an x, I'll substitute in a negative x, and wherever I see a y, I'll substitute in a negative y, and then I should get back the same equation. So we're going to substitute negative x and negative y and see if I get the same equation back. So let's try that. If I take x and substitute in negative x, and I take y and substitute in negative y, and that's equal to 4, well, a negative times a negative is always going to be a positive. So I am left with the equation x times y is equal to 4. And since this equation, after we do the calculation, and the original equation are the same, I can make the statement that this relation, or this function, has symmetry with respect to the origin. So let's build on this topic of symmetry. When we're talking about the parity of a function, we're talking about even functions or odd functions. So graphs that have symmetry with respect to the x, y, or origin can be classified as an odd or even function. And in actuality, graphs that have symmetry with respect to the x-axis don't actually do anything. So it's either going to be a graph with symmetry with respect to the y-axis or with respect to the origin, and that will determine whether or not the function is even or odd. So functions that are symmetrical with respect to the y-axis are called even functions. And the way that we figure out, and that means that they're going to be symmetrical with the y-axis, and then we perform an algebraic test to it. So if I have a function, f of x, and if I want to test to see if the function is indeed even, if I evaluate f of negative x, I should get back the original function. And then if I want to say that a function is odd, that is going to be a function that is symmetric with respect to the origin. So if it has rotational symmetry, it is an odd function. And the way that we test that is that for every x in the domain of f, if I evaluate f of negative x, I should get back a negation of the original function, or as if I were to distribute a negative into the entire function. Let's try an example with it. So graph each function and analyze the graph to determine whether each function is even or odd, or neither, and then we'll confirm it algebraically. So if I look at the graph of x cubed minus 2x, my graph is actually going to be right here. And so if I look at my graph, it looks like kind of like it's a cubic curve. It definitely does not have symmetry with respect to the y-axis. I can't fold the y-axis and get the original function back. But if I really wanted to, I could probably try to turn the graph around or turn it upside down and see if I get the original graph back. So I'm making a guess that this looks like an odd function. So let's actually support that claim algebraically. So for an odd function, I know that f of negative x is going to give me negative f of x, meaning if I plug in negative x into the function, what I should get back is the negation of this function, or as if I were to distribute a negative into this whole function. So let's try it. So I'm going to evaluate f of negative x, which means I'm going to take a negative x and plug it in wherever I see an x. So that's going to be negative x cubed minus 2 times negative x. Okay, well, let's use what we know. A negative number, any negative number that is raised to an odd power is always going to give me a negative number back. So I know that negative x cubed is actually going to be negative x cubed minus 2 times negative x. Well, negative 2 times negative x is going to be positive 2x. And so this is f of negative x. And in order for this function to be an odd function, I have to evaluate negative f of x and see if I get this function back. So let's try it. That means I'm going to take a negative and distribute it into the whole original function. And when I distribute the negative, I get negative x cubed plus 2x. Well, this function that I just did, which is negative f of x, and the function that I got when I evaluated f of negative x are the same. Because of that, I can say that this function is odd because it has rotational symmetry and f of negative x is equal to negative f of x. Let's try another one. So I have x to the fourth plus 2. So I look at the graph of that function, that's going to look like this. It definitely looks like it has symmetry with respect to the y-axis. It doesn't have rotational symmetry. So I have a feeling that this is going to be an even function. So if we know what we know about even functions is that when we evaluate f of negative x, or if I plug in negative x into my function, what I should get back is the original function, f of x. So let's try that. First I'm going to evaluate, in this case it's not f of x, it's g of x. So I'm going to evaluate g of negative x, which means wherever I see an x, I'm going to stick in a negative. So you get negative x to the fourth plus 2. And what you should know is that whenever you take a negative number, you raise it to an even power, what you're going to get back is a positive number. So this is actually going to be the same as x to the fourth plus 2. And this is g of negative x. Well, I know that the function that I just evaluated and the original function are the same. So what I am allowed to say is that this function is even because it is symmetric with the y-axis and f of negative x is equal to f of x, meaning I got the original function back. Let's try the last one. So I have h of x is equal to x cubed minus 0.5x squared minus 3x. Well, I know that the graph of this function is going to look something like that. And what it does look like is it looks like it does have odd symmetry or rotational symmetry. So I know that I'm not going to have to do my even test for it, but I am going to have to do my odd test for it. So if this is odd, I know that f of negative x is going to give me the same thing as negative f of x. So let's start and deal with f of negative x, or h of negative x. I'm going to evaluate h of negative x, which means wherever I see an x cubed or an x, I'm just going to plug in a negative. So this will be negative x cubed minus 0.5 negative x squared minus 3 times negative x. Negative x. Okay, well let's evaluate this and clean this up. So I know that any value that's raised to an odd power, or any negative value raised to an odd power, is going to give me a negative. So this will be negative x cubed. Negative 0.5, or I know that any negative value raised to an even power is going to give me a positive. So this will be 0.5 times positive x squared, or negative 0.5 times positive x squared. So this is going to be minus 0.5 x squared. And then negative 3 times negative x is actually going to give me a positive 3x. And this is going to be h of negative x. The next thing I have to find is I have to find h of negative h of x. So let's evaluate that here underneath it. So negative h of x is going to be negative 1 times x cubed minus 0.5x squared minus 3x. And when I distribute out my negative, what I do get is I get negative x cubed plus 0.5x squared minus 3x. Now this does look very close, but it's not, because if you notice in the for h of negative x, I have minus 5x squared, and in negative h of x, I have positive 5x squared. So these two functions, or this function, is neither even nor odd, because this function is neither even nor odd, because it is not symmetric with the y-axis, and it failed the odd test, which means f of x, or f of negative x, does not equal negative f of x.